Hey everyone, Team Google is happy to present to you our project about tweet prediction. This project consists of a competition created by Kaggle with the aim of predict which tweets are about real disasters and which ones are not. Twitter has become an important communication channel in times of emergency. Expanding the use of smartphones allows people to announce an emergency that they observe in real time. This is why more and more agencies are interested in programmatic monitoring of Twitter. But it's not always clear if a person's words really announce a disaster. This is where we go into action by creating the most efficient model possible to predict whether the tweet is about a disaster or not. For our project, we had 3 files: a training set, a test set, and a sample submission to submit our solutions. The tweet information we have at our disposal are the text of a tweet, a keyword from that tweet, and the location where the tweet was sent from. In order to build our model correctly, we proceed in different steps: exploratory data analysis, data cleaning, and machine learning. And now, let's move to the exploratory data analysis phase. First of all, we analyze the types of data contained in our dataset. We can see that the set of the elements are objects are part of the identifiers which are of the integer type. After that, we listed the different locations in order to get a global ID. Then, we displayed only the items that were not a real disaster, and then we did the opposite. These steps allow us to get a global ID of our dataset. Next, we check the distribution between the real and non-real tweets. We can see that there are a bit more non-real cases, but the sample is quite balanced, so there is no need to upsample the minority class. In order to get a better idea of the elements that differentiate the tweets from a disaster and those that are not, we analyzed the structure of each tweet. For example, here we can see the distribution of the number of words in each case. There is no difference based on the total number of words contained in a tweet from real and not real disaster. Afterwards, we displayed the distribution of the location. It seemed that location does not affect whether the tweet was about a real disaster or not. Once we saw that location seems not to be relevant to classify the tweet, what we are wondering now if tweets from a given location follow any right command pattern. Our findings show us, in general, tweets of not real disaster tend to have more grammar error and invented words rather than those about real disasters. We did few analyses to get a better idea of our model. Finally, we analyzed the frequency of words in the text of a tweet. This analysis allows to list the most recurring words in the text of a different tweet. We first list for real cases and then for those which are not. In order to obtain an efficient list of disasters, we have to establish 2 lists, one for real and a second one for not real disaster. Then we subtract the list of cases where we are not interested in order to have a final list.
Commonly, informal language contains abbreviations. We consider it relevant to substitute those abbreviations for the real meaning. The idea is to try not to lose any hide information behind these abbreviations, especially when applying n-gram. Then we noticed that there were duplicates but with different targets. We grouped them together and we averaged the target. We can see here that the first tweet is repeated 6 times and the average of the target is 0.33. Thus, we modified the target in our trend data. We set at 0 if the average is less than 0.5, else we set at 1. Concerning the preprocessing data, we removed URL, HTML tags, token nodes containing alphabet characters, token with equal or less than 2 characters, stop words, and punctuations. We also applied stemming and lemmatizing.
Once the noise is removed from the tweets and they are tokenized, we split the dataset into two subsets that are train and test, and then we vectorize the text process using both methods, counter vectorizer and TF-EDF vectorizer. Having said that, let's analyze the results for the 5 main single methods we have used. On the left, we have our position recall graph for each classifier. Recall is provided as the x-axis and precision is provided as the y-axis. As you may see, the best two classifiers are random forest and CVC, since as higher is the area below the curve, better is the estimation model. In the graph, we observe that when we are reducing the threshold, some methods like logistic regression don't add any true positive but only false positive, thereby lowering the precision. That's the reason the curve is not smooth. Finally, we observe that there is no dominant vectorizing method in terms of accuracy achieved.
In our project, we used ensemble methods. They are techniques that use predictions from different machine learning algorithms. We call them base models or weak learner. These models are then combined to form strong learners. The idea is that thanks to correct combination of weak learners to find better predictions. The objective is to increase the accuracy of predictions and robustness of models compared to predictions using individual models. And this is of course the advantage also. But why not always using ensemble methods? Well, computation time is higher and models are harder to interpret. Another disadvantage is that ensemble methods do not always improve predictive performance. Let me quickly present to you the 3 main ensemble methods we used in our project, which are bagging, boosting, and voting. Bootstrap aggregation or bagging first creates random samples of the training datasets with subsets of the training dataset. Then, for each sample, it builds a model, one of the algorithms we used before, and finally combines the different results of the models using voting. It combines base models of the same time and builds them separately. All models get the same weight. Boosting is similar to bagging in the sense that it uses voting and combines models of the same time. But boosting is a sequential technique where the first algorithm is trained on the entire dataset. Then, the following algorithms are built by fitting the residuals of the first algorithm. This means that we will give higher weight to the observations that were poorly predicted by the previous model. Voting aggregates the predictions of each classifier and predicts the class that gets the most votes. For hard voting, a majority vote is used for classification. For soft voting, we can set weights to give more priorities to certain classifiers according to their performance. Here I will show you the ensemble methods we used in our notebook. So we started with the bagging classifier using these different base models, and we see that we found the best accuracy using the base model random forest classifier in bagging. And we used the count vectorized dataset. Then we used other classifiers such as the extra trees classifier, AdaBoost classifier, which is part of the boosting classifiers, and voting classifier. Knowing here for the voting that we used once the hard voting and the soft voting. And we can see here that we found the best result using the voting classifier, and which was the hard classifier. And we used for that the count vectorized data. In conclusion, we can say that ensemble methods produce more accurate solutions than a single model would, but not always. If models have high variance, meaning overfitting of data, we need to use bagging. If models are biased, we should use boosting. Each ensemble method has its own advantage and weakness. Therefore, it's important to choose the right method. Some disadvantages also of ensemble methods are that they have higher computation time and reduced model interpretability. What we learned also from this project is that data cleaning and tokenization also influence the accuracy of our predictions. Therefore, choosing them carefully is important as well. Thanks for listening!